This is the third and final video on section 2.5, the cross product. I left this note up here, note 64, because we're going to use it in our first example and we're going to use it in our first formula. So I left this up here. And so we look at theorem 65. If we have the parallelepiped defined by three vectors, u, v, and w, so think of it as a three-dimensional parallelogram. Three-dimensional if two of your vectors aren't parallel. If they are, it's just flat and the volume is going to be zero anyways. But assuming you have this three-dimensional object, not flat, so its volume is going to be some positive number. The volume is going to be the absolute value of the dot product of u with the cross product of v and w. And we have a formula for this. We know that this calculation is the determinant of the matrix where we take the components from our vectors and make these the rows of our matrix. So this calculation is this determinant, and so we take the absolute value of this number, that is our volume. Now this is notation for a determinant, and it might be positive or negative. When you look at this theorem 65 in your notes, you're going to see a double bracket. It looks like this, and it has something that looks kind of like the norm there. What that is the inside bracket is for the determinant and the outside bracket is the absolute value. So what I'm saying there is take the absolute value of the determinant. You take the absolute value because volume's never negative. So example 66, we want to find the volume that's determined by u, v, and w. And so I'm going to start just by calculating the dot product of u with the cross product of v with w. Keeping in mind, this is just notation for the determinant. This number might be negative. So we start by making a matrix whose rows are the components of our vector. We're going to calculate the determinant of that matrix. So we look at 1, ignore the row, ignore the column. We have 1 multiplied by 6 minus 0. Then we take 2, ignore the row, ignore the column. We have 2 multiplied by 0 minus 0. We subtract because it's the middle column. And then finally, we have our negative 4, ignore the row, ignore the column. And so we have 0 minus 1. So we have 0 minus 1, we multiply by negative 4. We add these three numbers, and we have 10. 10's positive, so we're good with that. If our answer were negative 10, we just take the absolute value of that. So that is our volume. Then we have theorem 67. This is a nice theorem. It's going to come in very handy in the first section of the next chapter. So in chapter 3.1 on planes, we're going to use this theorem. But the idea is the cross product of two vectors is orthogonal to both of your vectors. So the cross product of v with w is orthogonal to v, and v cross w is also orthogonal to w. So if you have two vectors and you want to find a vector that's orthogonal to both, and sometimes you do, you take the cross product. And that vector is orthogonal to both of your vectors. The proof of that is given in your notes, so I'm not going to walk through that proof. Note 68, what is torque? Torque is the cross product of the position vector with the force vector. So if you remember the commercial, the car commercial with the kid and his dad, and the kid says, what is torque? And his dad tries to explain torque, and you listen to that explanation, he actually talks about the cross product. And so torque is the cross product of the position vector with the force vector. Okay, so I should have this up here because I forgot my forgot my mark here. So remember, cross product is a vector. So this is a torque vector. So the magnitude of the torque vector is going to be the magnitude of the cross product of R and F, and that is this. Why is that? Remember what sine of theta is. Sine of theta is going to be the magnitude of the cross product divided by this product right here. And so that's just using the sine formula, doing some algebra there.